In this segment, we'll continue our discussion of Markov chains, and in particular, we'll deal with ergodic sets and two important properties of Markov chains called irreducibility and aperiodicity. We'll begin by discussing higher order transitions, then define ergodic sets, talk about persistent and transient states, and then introduce the properties of irreducibility and periodicity. And this will help lay the foundation for our discussion of uniqueness and stability of invariant distributions. So consider a Markov chain, which is a sequence of random variables xn, with state space S, transition matrix P, and initial probabilities pi 0. We define the nth order transition probabilities as follows. Pijn is the probability that if we begin in state I, we'll be in state j after exactly n steps. And that's equal to the expression shown on the slide, which is the sum of the probabilities of every possible path that can take you from I to j in n steps. So we're summing here over all possible intermediate states k1 to kn-1 that you can take on a path from I to j. Now you should verify that the transition probability Pijn is the entry in row I and column j of the matrix P to the n. And you can check this very easily for n is equal to 2, in which case Pijn is simply the ith row of P multiplied by the jth column of P, which is precisely the entry in position ij of P squared. Now you should convince yourself that this is also true when n is larger than 2. Now let's look at an example to illustrate higher order transitions. So recall the Bernoulli-Laplace model from the previous segment with R is equal to 4. And you can check that the transition matrix in this case is as shown on the slide. If you're at a boundary state, then you move away from the boundary with probability 1. Otherwise, you can move up or down one step with positive probability, or you can remain where you are. Now here are the two-step transition probabilities. This tells you the probability that you'll be in state j after 2 steps if you're currently in state I. And similarly, here are the three-step transition probabilities. You can see that you can't reach one boundary from the other in 3 steps, but you can reach every other state. And in 5 steps, you can reach any state from any other state. Now look at the 10-state transition probabilities, which you see at the bottom of the slide. And here you see that the rows of the matrix appear to be converging to the same distribution. Now what this tells us is that the probability of being in state 3 after 10 periods is a little over 51%, regardless of which state we're in currently. In other words, there appears to be a history independence of the likelihood of finding oneself in a particular state, provided that one looks at nth order transitions when n is large. Now let's define ergodic sets. A set E of the state space is said to be ergodic if for each element I of E, the sum of the transition probabilities Pij for j also in E is equal to 1. And furthermore, if no proper subset of E has this property. Now this means that if you enter an ergodic set, you'll never leave it. And furthermore, for a set to be ergodic, it should have no proper subset with this property. Now a Markov chain may have multiple ergodic sets, and we'll see some examples in a moment. There may be states that belong to no ergodic set, and again we'll see examples in a second. And in the Bernoulli-Laplace model, the only ergodic set is the state space itself. And you should verify that this is in fact the case. Now one property of ergodic sets is that distinct ergodic sets must be disjoint. In other words, two distinct ergodic sets cannot share any elements. The proof is straightforward. Suppose that E1 and E2 are ergodic sets with a non-empty intersection, so they share at least one element. Let I be such an element. Since I belongs to the intersection, it also belongs to E1, and since E1 is ergodic, the transition probability Pij must be 0 for all j not in E1. Now repeat the same argument for E2, and you see that Pij must be 0 for all j not in E2. Now this means that the transition probability from I to j can be positive only if j belongs to the intersection of E1 and E2, which means that this intersection is itself an ergodic set. And we know that an ergodic set cannot, by definition, have a proper subset that's ergodic. So therefore the intersection of E1 and E2 must be precisely equal to E1 and also equal to E2. In other words, E1 and E2 can't be distinct. Now let's look at some examples. Here's a Markov process with two ergodic sets. If you begin in state 1 or state 2, you can never reach states 3 or 4. And similarly, if you begin in states 3 or 4, you'll never reach 1 or 2. And if you take the limit p infinity of the matrix of higher order transitions as n goes to infinity, you'll see that unlike the Bernoulli-Laplace model, only within ergodic sets do you find rows converging to the same value. Now another example. Here's a Markov chain with a unique ergodic set, but state 1 doesn't belong to that set. Again, if you look at higher order transitions as n goes to infinity, you see that rows corresponding to that ergodic set converge to each other and to some probability distribution over states, whereas the first row just converges to a vector of zeros. Now we'll define transience and persistence. So conditional on an initial state x0 being equal to I, the transition probability Fijn is the probability that you'll reach j from state I for the first time after n steps. So this is the probability that xn will equal j, while none of the other realizations x1 to xn minus 1 equal j, conditional on x0 being equal to I. So this is the probability of a first visit to j after n periods if you start in state I. And the probability that you're going to reach j eventually from state I is just the sum of the probabilities of these first visits, summing across all possible values of n. And we define a state to be persistent if Fii is equal to 1. In other words, if you start in state I, you'll eventually come back with probability 1. And we say it's transient otherwise. If we go back to this example, you should verify that the first state is in fact transient, while the other two states are persistent. Now we'll define the two concepts, irreducibility and aperiodicity, that we'll need in order to examine uniqueness and stability of invariant distributions. We say that a Markov chain is irreducible if for every pair of states I and j, the transition probability Pijn is positive for some n. Now what this means is that you can reach state j from state I with positive probability as long as you wait long enough. A persistent state I is visited infinitely often and satisfies the equation shown on the slide. Now you can verify that all states of a finite irreducible Markov chain are in fact persistent. Now if you have an infinite number of states, you can have an irreducible Markov chain in which all states are in fact transient. And an example of this is the three-dimensional symmetric random walk. So if you think about a particle at the origin in three-dimensional Euclidean space, and it could move along any one of the three dimensions one step in any period, you can check that this is in fact an irreducible chain, but one in which there's a positive probability of never returning to the origin once you leave. Now interestingly, this is not the case for symmetric random walks in 1 or 2 dimensions. In those cases, the probability of returning to the origin is in fact 1. This result is known as Polya's theorem. Now we'll define periodicity. We say that state I has period t if Piin positive implies that t divides n and is the largest integer to do so. Formally, the period of I is the largest common divisor of the set n for which Piin is positive. So if there's a positive probability that you can transition from I to itself in n steps, then n belongs to this set, and the period is the largest common divisor of all the integers in this set. And we say that a chain is aperiodic if all states have period 1. Now here's an example of an irreducible Markov chain, but one which is not aperiodic. It's irreducible because for any pair of states I and j, you can always reach j from I in some number of steps. But you should check that the period of every state in this chain is in fact 2 and not 1. For any state I, the probability Piin is equal to 0 if n happens to be odd. And if we take the limit of the higher order transition probabilities, we won't converge to anything. If we take the limit of p raised to even powers, you get the limit on the left, while p raised to the odd powers gives you the limit on the right. Now it's going to be important, as you'll see, to determine whether or not a given Markov chain is aperiodic. Now if you've already verified that the chain is irreducible, then all you need to do is to find one state that has period 1, because all states of an irreducible Markov chain have the same period. Let's prove this. If the Markov chain is irreducible, then for every pair of states ij, there exists some integers r and s, such that you can reach j from I in r steps, and you can reach I from j in s steps. This just follows from the fact that the chain is irreducible. Now it must be true that for any positive integer n, the probability of reaching state I from itself after r plus s plus n periods must be at least as great as the probability of going from I to j in r periods, then j to j in n, and then j to I in s. The right hand side gives you one possible set of paths that can take you from I to I in r plus s plus n periods, and so therefore it must have likelihood less than or equal to the left-hand side, which is the probability of all such paths. Now let Ti and Tj denote the periods of states I and j, and we want to show that Ti is equal to Tj. Now we know that we can reach state I from state I in R plus S periods, because we can go from I to j in R and then back again in S. So therefore Ti must divide R plus S by the definition of period. Now take any number n such that Pjj of n is positive. There must exist some such n because the chain is irreducible. Now in this case, the probability that you can reach I from I in R plus S plus n periods must be strictly positive. And this means that Ti divides R plus S plus n. Now we already know that Ti divides R plus S, so therefore Ti must divide n. Now we know that Tj divides n because you can get from j to j in n periods, so therefore both Ti and Tj divide n. But since Tj is the period of j, by definition it must be the largest common divisor of the set shown on the slide. And this means that Ti can't be greater than Tj. Now you can run through the exact same argument, reversing the roles of I and j, to get the inequality Tj is less than or equal to Ti. And these two inequalities of course imply that Ti and Tj are the same. So we've shown that all states of an irreducible Markov chain have the same period. And this is extremely useful because if you know that you have an irreducible Markov chain, and you can identify a state that has period 1, then all states must have period 1, and the chain itself must be aperiodic. Now we'll use these facts in the next segment when we discuss uniqueness and stability of invariant distributions, but I'll stop here for now.